I'm going to talk today about this paper that Mingji Liu and I published last year on our concept of the single neural network, which is a modified Baylor-Parnello neural network that is a little bit different than the original version. So the basic idea is shown in this little table of content graphic where imagine you have atoms A and B, and I'll show this in more detail later, but we have some vector of fingerprints here. So let's say there are 3 numbers depicted by these colored dots. These go into a single neural network, which is a nonlinear dimensional transform, into this new vector that has, say, 4 elements that are nonlinearly related to these ones. But what's special about this vector is that the atomic energy of atom A and atom B is linear in this vector space. And so we can get from a single neural network an energy for A and an energy for B, which we can add up together to get the total energy. So that's the simple idea. We applied it to a pre-existing data set on copper, germanium, lithium, molybdenum, nickel, and silicon, which are all pure single elements with some transition metals, with d electrons, some semiconductors, and simple metals that we used for the test set in here. All right, to understand what we did here, we go back to the original formulation of the Baylor-Parnello neural net. And what I'm showing here is an atomic configuration. And again, for each atom, we generate this fingerprint. And the fingerprint is just a vector of numbers that describes the local atomic environment. And in the Baylor-Parnello scheme, the yellow atoms have their own neural network and the blue atom has its own neural network. And the critical feature here is these 2 weights are not coupled with each other. They're totally independent. And this one will calculate the atomic energy of yellow atoms, and this one the atomic energy of blue atoms. And it's not that easy. We can't switch to green atoms in this formulation because we would need a 3rd neural network for that, and we don't have it, and we haven't trained it here. So what we did in our work here is we used this formulation. So we still calculate the same fingerprints, or a variation of them. They go to a single neural network here, where again we have that nonlinear dimensional transform into this space. But now in the outer layer we have multiple outputs, one for each element type, and that means that the weights in here are shared, and the latent space here that the energy is linear in has the proportionality constants in the outer layer that give us the specific energy yellow and energy blue atoms here. So we still add these up and get the total energy, and we still use this derivative formulation to do that. But now we have many fewer weights, which is beneficial for computational cost and for training. And we have an opportunity now to just add another output layer here to get green atoms, as long as we have some data to give us that proportionality. So that gives us some ability to think about having a transferable machine learned potential that way, and I'll talk a little bit about that when we go to the end. All right, so we basically use the same kind of Baylor-Parnello symmetry functions. There was a Gaussian function above right here that is like a Gaussian weighted distribution of the difference and this cutoff radius. So this is the distance between 2 atoms. And here we have, something that looks like angular contributions for triplets of atoms. We will often weight them, so we use a weighting function here, and that weighting function can be as simple as atomic number or electronegativity, etc. And that helps with transferability because it allows us to differentiate between the elements in the fingerprints, and then we can try to interpolate between them. Okay, so what did we do here? We took those fingerprints and we used 4 different approaches to build the machine learned potential. In gray, we have the original Baylor-Parnello network. In orange, the single neural network. Yellow is transfer, which means we trained on 5 of the elements and then predict the 6th. And then we also tried linear regression because you should always check if it's good enough. And you can see in some cases it's remarkably good, like with lithium. Very small errors. In nickel and copper, also small errors. It's always a bigger error than these other nonlinear models, but it is remarkable how good it is in general, which tells you that we have good fingerprints in general, and then the nonlinear dimensional transform just makes them better. So if we look across here, there's pretty good comparison in the errors. The biggest ones are always for molybdenum. We think that data set is the most sparse and has the most uncertainty associated with the predictions, which is probably why we see the broader range. So we get good results for energy, mean absolute errors, and forces. So 0.05 would be an EV per angstrom, a typical cutoff that we would use. And for some of these systems, they all work. And for others, we think there needs to be more data in the data set to make it better. We looked at a variety of different ways of splitting the data. So to give you an idea of how the machine learning works, we split our data set into training data and then leave some out for residual test data. That means we have to choose how to split it, and we do that with different random seeds. And so each one of these data points are the train test split for different seeds. And this gives you an idea of how reproducible is any one of these fits. And sometimes it's better, sometimes it's worse. And that just tells you that you can't use a single model and know what the answer is without exploring how important is the data that you're looking at. All right, so that brings me to this idea of being able to transfer the data. So what this means for copper is that in the case of transfer is that we would have trained on all these other ones and then predicted copper and so forth. And what we find is, like, by and large, it all works pretty well, and we get pretty good transferability between these. All right, so that brings me really here to the end. You can see, quite small mean absolute errors for some, like lithium, nickel, and copper, and then bigger ones for silicon and germanium. These have very different local environments than these simple metals, usually more like diamond structure instead of close packed metals. And then molybdenum is BCC. It's also quite different, and maybe has some kind of sparse data. So overall, we had pretty good results for being able to compare what we got for linear regression here. We have Baylor-Parnello here. This one always had the lowest, or almost always. Single neural network over here had quite good performance, and the transfer learning also worked out remarkably well. So that kind of is a nutshell summary of what the single neural network architecture is. It's basically a Baylor-Parnello network, but we have multiple outputs with shared weights, and that leads to the ability to do some transfer learning. And if you get nothing else out of this video, it might be that linear regression is surprisingly good in this work. So that is it for this paper. And we'll have maybe some more videos later that show how we use this single neural network architecture and idea for some follow-up ideas in molecular simulation. So I hope you enjoy reading the paper and that you learned something about how we build machine learned potentials. See you next time.